Now, how do we think about this capacity allocation problem here? First of all, in the rest of this lecture, when we say a flow, we mean a session, we mean the source, because we equate a session with a source, as each session traverses a single path that is already given to us, and a session has one source node and one destination node. So this is a unicast session over a single path. We're going to use these three words interchangeably: flow, session, or source. We're going to index each of them by, say, I. And routing is already fixed, so you cannot change what path will a session take. Okay? You can only change the transmission rate of the source of that session or flow, not the path that it takes. Now, the interaction between routing and congestion control, which we briefly mentioned in the last lecture in network architecture, you can think about that, and maybe in the homework problem you can encounter one of those. But for the lecture, fixed routing, you only adjust the degree of freedom for congestion control, namely the source rates. Now, this capacity allocation problem, we first have to make sure that the solution we propose is a feasible one, meaning that it can satisfy the link capacity constraints on all the links in the network. Otherwise, that vector is infeasible. It might be great to have, but you cannot accommodate that. There might be a single bottleneck link somewhere. And then there will be likely uncountable number of feasible allocation vectors. The question then is, which one should you pick as the optimal? Optimal with respect to what? Well, you want efficiency and you want fairness in this allocation. You don't want to waste link capacity. For example, assigning 0 to all the source as the rates. That's as a feasible solution, but clearly is very inefficient. You also want it to be fair. Let's take a look at an example. Okay, here is an example with 4 links, okay, and 4 nodes in a graph, and there are 3 sessions. So 4 links marked by 1, 2, 3, 4, and 3 sessions labeled by A, B, and C. Session A traverses all 3 links in this tandem. Okay, so from source node to destination node. Session B goes from this source to this destination, sharing one link with session A, and then go through another link by itself. Session C also share one link, session A. In fact, that is the only link that session C goes through. Okay. Now the question is, if I have a unit capacity on each of these links, then what should be the allocation of the capacity? Okay. So first of all, you need to be feasible. Okay. For example, I want to give all 3 sessions 1 megabit per second. So I want to give the vector 1, 1, 1 to sessions A, B, and C. Well, that's not feasible, right? Because then link 1 cannot accommodate 2 megabit per second. It only got a capacity of 1 megabit per second. Same thing for link 4. So you have to pick a feasible solution, and you start to think that, hey, maybe links 1 and 4 are kind of the bottleneck links, right? If they are saturated, then even if link 3 has leftover capacity, I cannot add more rates to session A, because the bottleneck might be on links 1 and 4 competing with the other 2 sessions. So it is not just about the number of links that you traverse. It's not like C goes through 1 link, B goes through 2 links, A goes through 3 links, and therefore, you know, A should get fewer rate than B, B should get fewer rate than C. It's really about what kind of links are you traversing. If you are using a lot of bottleneck links, then maybe you should not receive too much rates. And in that sense, we can see that A uses 2 bottleneck links, 1 and 4. B uses 1 bottleneck link, and C uses 1 bottleneck link. So maybe B and C even though B traverse one more link, should be treated in similar ways because the additional link B traverses is really not a bottleneck link. Okay. In the configuration of equal 1 unit, 1 megabit per second capacity for all 4 links. Of course, if you change that configuration, the implications can be different. Then we want it to be efficient. Now, it is actually impossible to fully utilize 4 megabits per second across all 4 links. Okay. But you can try to use as much as possible. For example, if I give session A 1 megabit per second and the other 2 sessions 0, okay, that is a particular allocation, right? It actually would use 3 out of 4 megabits available in the network. Here's another way. For example, I can give half megabit per second to the 3 sessions. That actually also uses 3 out of 4 megabit per second available in the network. Right? Because this link and this link will be fully utilized. That's 2 megabit per second. This link got half, this link got half for sessions A, B respectively. So if you look at these 2 vectors, they are both efficient. Okay? But clearly they look very different. In particular, this allocation actually starves sessions B and C, giving them 0 rates. So you probably think, this is unfair. Later in lecture 12, the last lecture of the course, we'll devote the whole lecture to quantifying notions of fairness. But you may remember alpha fairness. Okay? And this one looks more fair than that one. But you may think, gee, session A is actually taking up a huge amount of resources. So why should we treat it equally as if it's the same as sessions B and C, right? It goes through 2 bottleneck links, not 1. And indeed, if you go through the derivation of proportionally fair, you may remember if we do logarithmic utility maximization, we get proportional fairness. Then the answer is that you should give session A 1/3 of a unit. So 1/3 of a megabit per second, and sessions B and C 2/3. Again, the efficiency is that you are using 3 out of 4 megabit per second in the network. But the allocation is 1 unit of share for A, 2 units for B and C. And that conforms to our intuition that B and C should be treated about the same because they use 1 single bottleneck link, and A should not be the same because it uses 2. And indeed, you see a sense of proportionality, right? If you use twice as many bottleneck links, you will be given half of the capacity as the other sessions. And if you impose that condition, you can quickly see that this 1/3, 2/3, 2/3 will be the most efficient solution. So we want feasible solution and then strike a trade-off between efficiency in utilizing the link capacities and the fairness of allocating them among competing sessions. So now the question is, how do we formulate this problem in general? Let's first look at the constraints of this optimization problem, which is the link capacity constraint. We have to find a representation of the routing decisions, which is again given to us already. We don't get to change that, but we have to write it down because that clearly changes the configuration of what session uses what path, what links. There are a few different ways to do that. One is to say that if you look at each source, okay, is that a source that uses link L? For each link L, you can write out a subset of nodes, which are the sources that uses link L. Denote that set by S of L. And you can ask yourself, is node I in that set? Conversely, you can say, is link L being used by this source? Given the routing, you know for each source I, there is a set of links, a concatenation of which provides the end-to-end path. Is this link L in that path? Is it an element in the set L of I? Okay. There's yet another way to represent this in a matrix. Think about a number R, which is a binary number, 0, 1 sub Li. It is 1 if node I uses link L and 0 otherwise. So if link L is on the path used by source I, then RLI is 1, otherwise is 0. And soon we'll see an example illustrating this using the same topology that you just saw. So now I can write down the link capacity constraint by saying that multiply RLI by Xi, which is my source rate at source I, summing over all the i's. What is this? Well, we can give it a symbol. This is Y sub L, because we sum over all the i's, fixing a particular L. This is the load on link L. It's the load on link L. Okay? Or equivalent, we can write it as the summation of all the xi's, but summing only over those i's in the set of sources using link L. We can either represent it in this index way or represent it in this binary matrix way. And what we want is to say this load on link L should be no bigger than the capacity on link L, denoted as C sub L. So each link indexed by L got a fixed known number capacity C. Now you see that the routing matrix collectively called R and the link capacity vector, which we can put these numbers into a vector, C, are both given constants. R matrix and C vector are constants. We do not get to change the link capacities or the routing decisions. We get to change the X vector, hopefully distributively, that is the source rates. Okay. Y is just a shorthand notation of sum of certain X with respect to a particular link L. Okay. So we want a linear function of X called Y to be less than the capacity C. During the transient, this inequality will be violated as you try to search for the right loading on the link L. But at equilibrium, you want this inequality to be satisfied for all links L. Okay. Now, we can, of course, write this as a shorthand matrix notation. R matrix multiply X vector should be less than or equal to the C vector. So this is yet another way of shorthand notation to represent this link capacity constraint. Of course, this inequality is comparing two vectors, the Y vector and the C vector. So inequality here means component-wise. The first component is less than the first component, the second component is less than the second component, and so on. Okay. Now, what about the objective function? Well, the objective function here, as we just mentioned, can be alpha fair utility function. They capture both efficiency and a notion of fairness, parameterized by this alpha. So again, reminding ourselves from lecture 11 that the utility function as a function of the equilibrium rate acts at the source, parameterized by alpha equals x to the power 1 minus alpha over 1 minus alpha. If alpha is not equal to 1, if it is equal to 1, then in the limit this becomes log of x. Okay, so different sources I may have different alpha. So you can say this source has 1 alpha, another source has a different shape. Okay, or we can say they all share the same alpha, in which case we're just maximizing the summation of u times u of xi sub alpha, sharing the same shape, summing over all the sources I. And this will be the objective function. Maximize the sum u of xi, subject to the constraint of Rx less than or equal to C, and therefore we have our formulation of network utility maximization, NUM, and the num formulation. Maximize summation u of xi summing over I such that Rx is less than or equal to C, where the variables is the x vector collecting all the source transmission rates xi for a given constants, the routing matrix given and the capacity given, and say the shape of the utility function alpha given. If you look at this optimization problem, see that it is linearly constrained, and the objective function assuming smooth increasing and concave functions of a utility function, which is the case for alpha fair utility function. This is a concave maximization, which, as you may recall from lecture 4, is equivalent to minimizing a convex function, same as minimizing minus the sum of utilities. Okay, so instead of maximizing this, you are talking about minimizing this. Subject to linear constraints, and this is a nice problem. It is a convex optimization because you are minimizing convex function or equivalently maximizing concave functions subject to convex constraint set, which turns out to be a set of linear constraints inequalities. So it is a nice optimization, even though we didn't spend time talking about the exact algorithms that would belong to an operations research course. But you can believe me that there are very efficient centralized algorithms to solve it. Now, better still, and as needed in this case, we need more than just efficient centralized computation. We need a distributed algorithm to solve this efficiently. And that indeed turns out to be the case because this problem is so-called decomposable. Clearly, the objective functions is a sum of different sources utility, and therefore it is already decomposed. The problem, the trouble, resides in this coupling constraint. Okay? Each link is shared by many sessions, and each session traverses through many links, just like what we saw early in this example. Okay? So we cannot ignore those coupling represented by this Rx less than equal to C. But fortunately, we can do what we call dual decomposition. It's called dual decomposition because it's actually solving the so-called Lagrange dual problem. Give me an optimization problem, I can always derive so-called dual problem. And there are many strong, nice properties between the primal and the dual problem. One of which allows us to look for cracks in the original problem and solve it through solving the dual problem, and you get a distributed solution. This is a very interesting topic and is quite a powerful mathematical tool in designing networks of various kinds, but we will have to defer this to advanced material part of the lecture. Okay, so suffice it to say at this point that indeed this is a convex and decomposable problem, and we'll now present the distributed algorithm. If you want to see the derivation, please wait until the advanced material part.